Mm.
And I equals x squared dm. So you can usually calculate this by setting dm to be defined as the density times the distance or area or volume or whatever. And then you can integrate for I that way.
Mm.
Yeah.
For different situation, right?
Yeah.
On a rod, for a prey, for a hook, right? And then when it's not uniform, when it's a uniform situation, right? Okay. Rohan, you can continue. Talk about a pulley situation, how to apply an equation
The
on a
pulley stuff.
pulley. Mm.
You can set it up where like the summation of forces equals ma. Like that's what I'm trying to do. And then we kind of have the equation to the side.
Mm-hmm.
So like, yeah, just
Right. So when you consider the mass on the pulley, the rotation on the pulley or not, right? It's
yeah.
different, right? Mm.
Then yeah, you can just use like the m1g minus t1 equals m1a.
Mm.
And then yeah, like RT sine 90 minus RT2 sine 90.
Mm-hmm. And then you can apply in the horizontal pulley and pulley.
Oh, yeah, I actually questioned about that while I was doing the homework.
Oh, okay.
Like
What's your question?
when I was trying to do like horizontal versus vertical pulleys, I had to like look at the notes for like the actual like equations because I couldn't really like understand why it's different. Like why are they different, if you know what I mean? Like how why specifically in the equation is changed to like make it work for vertical and horizontal. I just didn't really understand that.
Well, are you talking about this pulley question?
Yeah.
Which one you get confused?
So like for example, like the R of T1 minus T2 equals I of
Mm.
8 over R.
Mm.
I'm confused. Like, is it the same for horizontal and vertical, or is it different? I
It's
feel
the
like
same.
okay, 'cause I was like thinking conceptually that may be different. Like when I just like look at it, I'm like I don't
Thi-
really know, but
This how do we get this equation? Is net torque equal I alpha,
yeah,
right? So which two forces create this net torque will be
tension and gravity.
T1 or be careful, not gravity. Gravitational force is applied on both mass. The
Oh,
these two masses they don't rotate. It doesn't rotate, right? The mass
mhm.
M1 doesn't rotate, M2 doesn't rotate. The only thing is rotating is the pulling. Then what force create torque? In order for it to rotate with a certain angular acceleration, you must have a net torque. So in this case, it's the two tension create torque, right? But
Yeah.
remember, these two tension, even though it's both going vertical, but for the horizontal pulley one, you have one force going horizontal. Why you can set up the same equation? Because torque, you only have clockwise or counterclockwise. You don't really have up and down, X and Y difference. You got it?
Mm-hmm.
Right? So in this case, the only thing you need to pay attention to if this force create clockwise torque or counterclockwise. It doesn't matter if pulling is vertical or horizontal.
Okay. Let me write that down.
Yeah.
Wait,
So it's
are there any formulas that will be changed if it's horizontal versus vertical? Because I think
uh
there will be,
if you
right?
are talking about a torque, you just
Yeah.
need to analyze if the torque created by this force is clockwise or counterclockwise.
Okay, so vertical versus horizontal doesn't matter, right?
Mm.
Okay, thank you.
You're welcome. You got it?
Yeah.
Mm. So this is a pulling situation. Consider rotation without consider the rotation. Okay. And then you can compare the acceleration and final speed when it's going down the ramp. Then you see these are two different situations. What are those two different situations?
Slipping versus frictionless, or without slipping versus friction.
Yeah, rolling without slipping and frictionless. Frictionless, remember, you have a sphere or you have block going down, that will be the same thing, right? If you put a block here, it will be the same thing. And remember how to set up equation to find the acceleration, find the final speed. You can use the kinematic equation or use the energy conservation. Does it make sense? You got it right? And then for the rolling without slipping, remember it's a static friction creating torque, not FG or FA, right? And then you can use the energy conservation for both. The difference is for the right side, you have both translational kinetic energy and rotational kinetic energy. That's why speed will be smaller. Do you see that? So this is rotational kinetic energy. Kinetic energy in the third part of rotation. So let's put it together for translational kinetic energy and rotational kinetic energy. You can take a notes, okay? So this one, when we talk about translational kinetic energy, there's a half mv squared, right? Correspondingly, rotational kinetic energy will be half I omega squared, right? And then working energy, what else did you know in working energy? What else do you know in working energy? Work. What does work depend on? F delta x cosine theta. F dot product, right? Dot product between F x. Correspondingly, how do you find the work when you are doing rotation? It will be equal to torque dot product of theta, right? Torque times delta theta. It's work, right? And then you can find the power will be equal to work over time. It's F times delta x over delta t, right? Similarly, power will be equal to work over time, which is torque times delta theta over delta t. So which is torque times omega. And then over here, this will be force times velocity. Right? That's power, no momentum, okay? This is power. This is only when V is a constant. Write it down. This is only when you have constant angular speed. And what else do you learn in working energy? Anything else? Anything else that you learn in working energy? Net work equals change in kinetic energy, right? You remember working energy theory. network equals change in kinetic energy. So you will get network will be equal to half m v final square minus half m v initial square, right? And then you will get network equals half I omega final square minus 1/2 I omega initial square, right? And then remember, we talk about this force versus X, right? You use the area under the curve, you get work, right? Similarly, you get torque versus theta. Torque versus theta. The area, what does it give you? You get work or change in kinetic energy. Does it make sense? If it's a network, right? Write down. That's how you compare, right? And then if you get kinetic energy or work versus X, the slope will be force, right? Kinetic energy versus theta, the slope will be the torque. Torque, right? So sometimes when you see the graph, remember always check what is given on y-axis and x-axis. Never assume, oh, this is x or anything you are familiar with, right? So graphing question is very common, yeah. Okay. Now, anything else you learn in this working energy? Remember, it's energy conservation. The energy conservation condition is still the same. Remember, when can you use energy conservation to solve the problem? What's the condition to use energy conservation, Jameson?
There's no external forces.
When external force is momentum. Momentum conservation you use external force, right? When there's only conservative force doing work. Right? Doing work. This is the same thing for both. You got it? Because when you are talking about gravitational force, it is also external force, right? Gravitational force. Good? So this condition is the same. And then what happens when you have non-conservative force doing work? So you can use the work done by non-conservative force will be change in mechanical energy. Got it? Good, right? And anything else? Working energy. So this is a key concept. We put it together here, right? Any questions so far? Working energy. Last time, did we talk about this question here? Let me see, huh? This one, did we talk about it? Did we do it? The bottom question? Did we have a chance to talk about this question? No, maybe not, right? Jameson, did we talk about it?
I don't think so.
No, okay. Now, let's do it right now. Let's do this question, okay? Rohan, you can read the question.
A solid cylinder with mass m, radius r, and rotational inertia 1/2 mr squared rolls without slipping down the inclined plane shown above. The cylinder starts from rest at a height h. The inclined plane makes an angle theta with the horizontal. Express all solutions in terms of m, r, h, theta, and g. Determine the translational speed of the cylinder when it reaches the bottom of the inclined plane. On the figure below, draw and label the forces acting on the cylinder as it rolls down the inclined plane. The arrow should begin at the point of application of each force. Show that the acceleration at the center of mass of the cylinder while it is rolling down the inclined plane is 2/3 gravity sine theta. Determine the minimum coefficient of friction between the cylinder and the inclined plane that is required for the cylinder to roll without slipping. The coefficient of friction mu is now made less than the value determined in part D, so that the cylinder both rotates and slips. Indicate whether the translational speed of the cylinder at the bottom of the inclined plane is greater than, less than, or equal to the translational speed calculated in part A. Justify your answer. Indicate whether the total kinetic energy of the cylinder at the bottom of the inclined plane is greater than, less than, or equal to the total kinetic energy for the previous case of rolling without slipping. Justify your answer.
So A, you can set up equation. What do you get for A? Mm.
We use energy conservation for A, right?
Yeah. Okay. So how do you set up?
M mass times gravity times height equals 1/2 mass times velocity squared plus 1/2 IW squared.
1/2 mv squared plus 1/2
1/2
I omega squared. Right?
omega.
And then you plug in what's the relation between V and omega to simplify it.
Um, it would be V over R.
V over R. So you get half m plus I over R squared times V squared. So you'll get V equals 2 mgh divided by m plus I over R squared. Got it? Name B, how many forces? How do you draw the force? How do you draw the force here? That's what we talked about earlier, right? Do you forget? Jameson, how many forces are applied on this cylinder, solid cylinder?
Gravity, normal force, and friction since it rolls without slipping.
So Fg going down, right? Now, did you set up equation to find the acceleration? It's normal force. Good. So C, how do you set up equation? You finish this one? Jameson, you set up equation for C?
Not yet.
Mm-hmm. What to set up the Newton second law. You use the net force equal
tan
MA.
theta, I got tan theta over 3, but I don't think I did it correctly.
Oh, so what did you do? How do you set up equation?
What I did is that I used Newton's second law. So like the gravity on the incline is mass gravity times sine theta.
And then,
And then setting the friction force to F, I did mg sine theta minus F equals ma.
good.
Yeah.
Then what's the second equation?
Torque, right?
Mm.
You do like the friction times the
So it'll be RFS, right?
yeah.
Equals I over RA, right?
Yeah, then
So you simplify here.
oh I get it where I get wrong now.
Oh, is it here?
Yeah.
You make a mistake? Oh, okay.
Yeah, I made a mistake here.
Mm-hmm. You done right? Yeah. So you will get 1 plus 2. You use 1 plus 2. So you will get mg sine theta equals m plus I over r squared times a. So your a is mg sine theta divided by m plus I over r squared. Mm-hmm. And then you plug in I, half m r squared, right?
Yeah.
That's how you get 2 over 3 g sine theta. Okay. Now let's see D. How do you do it? Jameson.
You'd probably have to do something with wait, do you? No, we don't have you, never mind.
Mm-hmm.
Wait, wouldn't it just be mu equals Fs over n because they're already perpendicular to each other?
So over here, because you are looking for minimum coefficient, right? So you can use Fs equal 1. mu as Fn, right? Mu as Fn, right? Then what is Fn? What is Fn? So you plug in Fs equals half m I over r squared is half m, right? Time a is 2/3 g sine theta. Jameson, what's the Fn? Normal force. Mg cosine theta, right? Right? On the ramp, right? Mg cosine theta, right? Good. So divide by mg. So you will get mu s equals 1/3 tangent theta. Done, right? Okay, now E. Try to see how to answer I. E, how to answer I? Question I.
It would be greater
It will be greater. Translational speed will be greater. Why?
because if it slips, then it's not rotating as much, and since the energy is 1/2 I omega squared, if it's not rotating as fast, there's more translational speed to compensate.
Good. Okay. Right? Right? Or you can also use this Newton second law, right? Right now, static friction will be kinetic friction. You have less kinetic friction according to Newton's second law. You will have greater acceleration, right? And it's going down the same ramp. That's why final translational speed will be greater. Okay, it's good. Then how about 2i? 2i, how do you do it? What will be the answer for 2i? 2i.
It would be greater because in the previous reasoning, I already said that V would be greater.
Oh, total kinetic energy is greater. Is it possible to have greater final energy?
Oh wait,
Is it
KE
possible?
is not just MV squared, right?
Mm. Total translational kinetic energy and rotational kinetic energy. Mm-hmm. Mm-hmm. So in this case, would be less than, right? You understand why it would be less than? Is it possible to be greater? No, right? Right? It's not possible to be greater, right? So over here in this situation, why the total energy is less?
Because friction is non-conservative.
Eh, yeah, non-conservative force doing work. So energy is lost. That's why it's less. Does it make sense? You got it? Any question? Any question so far? Okay. So this is rotational kinetic energy. Oh, did you write down everything? So 2I, how to answer it? Remember, this is kinetic friction. Earlier, if it's static friction doesn't do work, energy is conserved. But right now, it's kinetic friction. Kinetic friction is not conservative force, right? And then the kinetic energy in this situation, even though translational kinetic energy is greater, but rotational kinetic energy will be less than what you have earlier, right? So what you need to do, in this case, you need to mention energy is not conserved because there's a friction doing it. Okay? You done? Okay. Any questions so far? Yeah. Right? This rotational kinetic energy you will see. And now you look at this situation. Did we talk about this one last time? Rohan, Jameson, did we talk about this question? Last time we
I
didn't.
don't think so. I don't really
No,
No,
right?
I don't.
Okay, now you can look at this question. So you can see the difference. Jameson, you can read the question?
A block of mass m slides up the incline shown above with an initial speed v naught in the position shown. If the incline is frictionless, determine the maximum height h to which the block will rise in terms of the given quantities and appropriate constants. If the incline is rough with coefficient of sliding friction mu, determine the maximum height to which the block will rise in terms of h and the given quantity. A thin hoop of mass m and radius r moves up the incline shown above with an initial speed v naught in the position shown. If the incline is rough and the hoop rolls up the incline without slipping, determine the maximum height to which the hoop will rise in terms of h and the given quantities. If the incline is frictionless, determine the maximum height to which the loop will rise in terms of h and the given quantities.
So this is situation. First question, how to set up equation? A and B, how do you set up equation? A, are you done?
B naught squared over 2G.
Yeah. So this is the general situation. Just use energy conservation. You will get half mv squared equals mgh because it's a frictionless, right? So the h will be v naught squared over 2g. That's good. B, how do you set up equation? Mm-hmm. You got it? Or you want me to show you?
Can you show me?
Mm-hmm. So over here, what happened? You have kinetic friction. So is the energy conserved?
Yeah. Energy's cons-
Energy is not conserved. So you use work done by
Wait, but
non-conservative
it's
force.
frictionless, right?
Huh?
It's frictionless. Oh.
You have
Oh, I'm sorry. I took the okay, my bad.
you have friction, right?
Yeah.
Then it will
Okay.
be work done by friction, which is negative mu k mg cosine theta time delta x. That's work done by friction. And then final will be mgh minus initial will be total kinetic energy. Right, Jameson? You good, right? Then h delta x. So you can mu k mg cosine theta, delta x will be h over sine theta because you don't want to put too many unknown there, right? And then you are looking for the h, right? Divide by mass on both sides. And then you combine H, so GH will be 1 plus mu K cotangent theta equals V squared over 2, right? So you will find the new H will be equal to VO squared divided by 2G 1 plus mu K cotangent theta. Got it?
Okay, yeah. Yeah, okay, that makes sense. Thank you.
Mm-hmm. Okay. Got it? Jameson, got it? Any question? Okay. Now, C and D, you can set up a question. What do you get? Mm-hmm. So you use the initial equals the final will be half MVO squared plus half I omega squared will be equal to MGH. So you will find the high in terms of H. What is it? You're looking for H. You see that? It's 2h. Right? You see here? Because VO squared over 2g is h. That's why lowercase h is the 2h. The new height will be 2h, right? Okay. Then D, what's the answer? C, do you have any question, any concern here? No, right? Okay. So if you don't have any question here, then how about D? D will be the answer. Mm. Mm. Jameson, what will be the answer for D?
If they're the same mass, wouldn't it be the same because it's not rotating?
Will be the same as a block, right? If it's a frictionless situation, right? For the frictionless situation, it should be the same, right? Rohan? So it'll be same, right? So over here, if there's no friction, then still have mv squared equals mgh. So your h will be equal to VO squared over 2g, which is capital H. Does it make sense? We good, right? Any questions so far? For the rotational kinetic energy, anything confusing you? Anything confusing you?
Wait, for the last two bits on part C, how did you get there? Because when I did the wait, okay, yeah, never mind. I see where I went wrong.
A hoop, right? The hoop is
Yeah,
mr squared. You probably
yeah.
plugging the wrong iron, that's why, right? Then you will realize if right now hoop change to a plate, change to a sphere, solid sphere, then the situation will change, right? The situation will also will change. So this is a different question you will see. Later we'll look at this question, okay? Let's take a break, 5 minutes break. If you need to use the restroom, you can go right now, and then later, after we come back, we'll talk about angular momentum questions. Okay? Give you a break so that it will be more fast. Mm-hmm. You got it? So MV, right? Is angular momentum. Then angular momentum is this is similar to torque, right? Torque equal R F sine theta. And it's also a vector, right? Right? the torque or the angular momentum, what's the direction? It would be either clockwise or counterclockwise. Got it? Okay, so for momentum, what else do you need to know? You remember momentum? What else do you know? Mhm.
For like linear momentum or for like
Linear momentum and angular momentum. Momentum. You also need to know, what is it? Impulse, right? Remember what's impulse?
change in momentum?
Impulse equals change in momentum. Change in momentum, remember m delta v, right? We derive, you will get f times delta t, right? So you will get p equals f dt, right? Correspondingly, change in angular momentum will be equal to torque times dt, right? Or torque equals dl dt. F here will be dp dt. P is the momentum, no power. Got it? And then remember in this case, you will also see the torque versus time. Area, you get change in angular momentum, right? Force versus time. Area, integration, you get the impulse, change in momentum, right? Make sure you write it down. Okay? Write it down. And then same thing, right? P versus time, the slope, you get force. Every time you talk about the relation between two quantities, you always need to relate it graphically. Right? That is impulse, right? And then what else do we need to know for momentum? What else? Remember what else? Anything else? Remember? In momentum is a section. Okay. Collisions, right? Collisions, you talk about momentum conservation, right? Remember, when can you use momentum conservation? When your external force equals zero, then momentum is conserved. Correspondingly, over here, net torque is zero when you can consider angular momentum conservation. You see that? How many type of collisions you know? How many types of collisions?
Two,
Two. One of the two.
elastic and inelastic.
So elastic. Elastic. What kind of collision is elastic? What kind of condition is it?
Both kinetic and momentum are conserved.
And momentum is conserved. And kinetic energy is also conserved, right? But inelastic is write it down, okay? Remember to write down. Momentum is conserved, but kinetic energy is not conserved, right? So right now, when you do this question, so you are going to see what is conserved. Angular momentum conserved, linear momentum conserved, or kinetic energy conserved. Depends, right? You got it? Hmm. Write down everything. So we are going to talk about a few questions here. All right? Look at the question first. Now try to see in this case is energy is conserved or momentum is conserved in this case. So how do you set up an equation? First, angular momentum is conserved. Why is angular momentum conserved? This situation, you have force applied in the rotational center, right? Does it create torque?
No, because sine 0 is 0.
It doesn't create torque, right? Or equal zero, right? So right now, you can use angular momentum conservation. So Li equals L final, right? So how do you find the initial angle? Initial angular momentum. Initial angular momentum. So it will be I omega. And then final angular momentum, you use L M2V RP sine theta. Does it make sense? So you can find that V will be equal to I omega divided by L M2, right? What is I? 1/3 ML squared. And then divide by L M2. So you'll get M1L over 3M2, right? This one I just show you how to do it. Any question here? So you know that initially the rod is rotating, right? So this is the whole body rotating. And you are given omega, so you can use I omega directly. But after collision, the rod stop, M2 continue, right? So be RP sine theta, right? The linear momentum B. Any question here? Any question here, Jameson? Rohan? Now you can find linear momentum initial would be equal to M1 time V, because it's a whole body, right? So you use V center of mass. It would be center, right? For when this object is moving, is rotating, everywhere on the rod should have the same angular speed, right? But linear speed will be different with a different arc, right? So we will use the center of the rod. So you use half M1 L times omega. You see that? Now, can you find the linear momentum on the system after collision?
If you already have the velocity, can't you just use that?
Yes. So if P final will be equal to M2 times V, you get the final, right? So you can see there's a half M1/3 ML omega. So it's a linear momentum. Is the linear momentum conserved? Okay, D. D, how do you answer it? James?
One minute. Wait.
Why linear moment? Is linear momentum conserved?
No.
No, right? Because it needs 1/2, needs 1/3. They are not the same. So why linear momentum is not conserved?
Because it's rotating, so it's although for that one it's at L/2, the other one is like rotating, so the velocity would be different where it hits.
It's because there's an external force applied here and a hinge, because it needs to fixed at point P, right? So when the rod is rotating, then there's an external force applied and a rotational center, right? And then earlier it just mentioned, oh, angular momentum is conserved because neither force is applied and the rotational center. Neither force doesn't create torque. R will be 0, right? You good? So this question, no problem? Okay. So let's look at the second question and see what's the difference, right? Rohan, you can read the question.
A thin, uniform rod of mass M1 and length L is initially at rest on a frictionless horizontal surface. The moment of inertia of the rod about its center of mass is M1 L squared over 12. As shown in figure 1, the rod is struck at point P by a mass M2 whose initial velocity v is perpendicular to the rod. After the collision, mass M2 has velocity negative v over 2, as shown in figure 2. Answer the following in terms of the symbols given. Using the principle of conservation of linear momentum, Determine the velocity v of the center of mass of this rod after the collision. Using the principle of conversion of angular momentum, determine the angular velocity omega, of the rod about center of mass after the collision. Determine the change in kinetic energy of the system resulting from the collision.
So in this case, what's the difference? What's the difference right now? You can see right now, this is not fixed. So there's no external force. That's why both linear momentum, angular momentum are conserved. Okay? So linear momentum is conserved. So let's set up equation. So it will be M2V, right? Will be equal to M2 negative half V, opposite, right? And then plus M1V prime. So you will get, so you can find that V final will be equal to 3M2V over 2M1. You got it? Right? This is linear momentum conservation, right? Now, how do you set up angular momentum conservation? Angular momentum right now, initially M2, right? So remember, this is point mass, right? What equation do you use to find the angular momentum? What equation? RP sine theta or I omega? Johan,
The what?
which equation do you use to find the initial angular momentum?
Initial angular momentum.
Mm. Mm-hmm.
I have like 2 seconds to look through my notes.
Huh?
Can I have 2 seconds to look through my notes?
Okay. Mm-hmm. So this is a point mass situation, right?
Is it the moment of inertia times the angular velocity?
I omega, right? I
Yeah.
omega normally you use it for the rod, but right now it's a point mass M2. So you use RP sine theta, right? RP sine theta, what's R in this case? R right now should be half L minus L over 6. So you get 1 over 3L. Okay? So be 1 over 3L R M2V, right? Then will be equal to 1 over 3L times M2 times negative half V, right? And then plus I omega. And you add it, right? Mm-hmm. Then you can simplify it. L M2V over 2 will be equal to 1 over 12 M1 L square omega. So you'll get omega will be equal to 6 M2V over L, right? Mm-hmm. Now B, Jameson, how do you set up an equation to find a change in kinetic energy? C.
Wouldn't wait, it would just be the original I omega, 1/2 I omega squared, and then plus 0 since, wait, no, not 0. 1/2 m2 v squared, and then it's equal to
So right
the new
now,
one.
are they equal? Change
No.
is the final minus initial, right?
Yeah.
So you use a half m2 half v square, right? Plus a half m1 v prime square. Yeah, oh, final, right? Anything else? Half I omega square. You plug omega here, right? That's all final. Minus initial will be half m2 v square. You see that?
Wait, for the final one, wouldn't the velocity be like b over 2 since oh wait, no, never mind, it's already there.
Yeah, v over 2, right? Good. You're done? So you can find a kinetic energy here, right? You good? You done everything? You done right? Okay. And now, there's one more question. Let's look at this question. Let's see. James, you can read the question?
A system consists of a ball of mass m sub 2 and a uniform rod of mass m sub 1 and length d. The rod is attached to a horizontal frictionless table by a pivot point at point P and initially rotates at an angular speed omega, as shown above left. The rotational inertia of the rod about point P is 1/3 m sub 1 d squared. The rod strikes the ball, which is initially at rest. As a result of this collision, the rod is stopped and the ball moves in the direction shown above right. Express all answers in terms of m sub 1, m sub 2, omega, d, and fundamental constant. Derive an expression for the angular momentum of the rod about point P before the collision. Derive an expression for the speed v of the ball after the collision. Assuming that this collision is elastic, calculate the numerical value of the ratio m sub 1 over m sub 2.
So in this case, is linear momentum conserved?
Yeah.
This is a fixed at this point, right? So linear momentum is not conserved because there's an external force. As long as this rod is fixed at one point, right? So angular momentum is conserved, but linear momentum is not conserved, right? So you can find A, right? A initial will be I times omega. Will be 1/3 m1 d squared times omega. Initial angular momentum, right? And then how do you find B? You use the initial angular momentum equals the final angular momentum, right? So it will be I omega equals dm2 v final, right? Right? So your v would be 1/3 m1 d squared, and then divide by dm2 omega, right? So you'll get m1 d omega over 3m2. That's m2. That's a v, right? And then it tells you the collision is elastic. So you need to find a ratio. So What is elastic? Right? So use kinetic energy initial equals kinetic energy final. What kind of energy does it have initially, Jameson?
Rotational.
Rotational, half I omega squared. And then the final kinetic energy is on the M2, right? You got it? So it'll be M1 squared, D squared, omega squared divided by 9 M2 squared, right? D squared, omega squared cancel out. M1 so you'll get M1 over M2 will be equal to 3, right? Is M1 over M2? Yeah. So is it 3? Right? You can find a ratio like that. Good?
Wait, how does the elastic affect this?
Huh?
Like, because it's elastic,
Yeah.
is it like the energy is like conserved or
Yeah.
okay?
Because the question tell you it's elastic. So you can use a kinetic energy is conserved.
Okay.
Initial kinetic energy equal final kinetic energy.
All
The
right.
question has to tell you it's elastic to use this equation. Okay?
Mhm.
Now, how about D? How do you do D right now? Did you write down everything here, Jameson? Rohan, you good? Okay, now let's do D. Do D right now. Any question? Anything confuse you? So right now, D, can you set up equation? Let me put it here. So you can set up equation right now. So over here, how do you set up equation? So you need to set up kinetic energy is conserved. And angular momentum is conserved too, right? So the first equation half I omega squared, right? And then half M1 V squared, right? It's still elastic, okay? Now, Jameson, the angular momentum conservation, how do you set up?
Initial equals final.
So it will be I omega, right? Equals X M1 V. And then you can plug in, right? So I is a 1/3 M1 D squared. So V will be equal to D squared over 3X, right? Then you can plug in here 1/3 m1 d square omega square equals m1 v square, right? So you can plug in here. So it'll be 1/3 d square omega square. And then it will be d power 4 over there's the omega here. And then 9x squared, right? So you can cancel out here. So you get x squared will be equal to d squared over 3. X will be equal to d over square of 3. Got it? Got it? You done? Any question here? Anything confuse you? Get right?
Hey, can you leave it up for like 1 more minute so I can copy it down?
Okay. You done?
Yeah.
Okay. Yeah. Okay. So this is the angular momentum application, right? Now let's look at this question here. Multiple choice question. Any question about this angular momentum? Now, question one. Rohan, you can read it?
An ice skater spinning along a vertical axis with the arms fully extended. If the arms are pulled in closer to the body, in which of the following ways are the angular momentum and kinetic energy of the skater affected? Angular momentum, A, increases, kinetic energy increases. B, angular momentum increases, kinetic energy remains constant. C, angular momentum remains constant, kinetic energy increases. D, angular momentum remains constant, kinetic energy remains constant.
So in this case, what will be the answer?
I think that the angular momentum would remain constant,
Mm.
kinetic energy would increase.
Angular momentum will be constant, right?
Yeah.
Then how about kinetic energy?
I think it would increase.
It will increase, right?
Yeah.
It will increase, right?
Yeah.
Mm-hmm. Right, Jameson?
Yeah.
So it'll be angular momentum remain constant, kinetic energy increase. That's good. Okay.
Wait, actually, I thought if you had like your arm spread out and then wait about
Your arm
oh, it says
out.
because I thought when you bring it in, you spin faster.
Mm. So when you have arm out, right? Your eye is bigger, right? Right? Your eye increase, so omega decrease. But angular momentum remain the same because net torque equals 0. mg doesn't create torque, right? Then kinetic energy, what equation do you want to use? You use L squared over 2I. Right? Angular momentum is the same, right? With a smaller I, kinetic energy is bigger.
Oh, yeah, wait, yeah, because I was just thinking about kinetic energy has to be like linear because for some reason.
Mm-hmm. You got it? You got right? So kinetic energy will increase because when you pull your arm closer, that's why your kinetic energy is smaller, right? It's bigger, right? Good. Jameson, any other question here? No, right? It's good. Mm-hmm. Yeah. So this is the way how you apply the equation. Now, how about question two? Question two. Jameson, you can read the question quickly. Mm-hmm.
A particle of mass m moves with a constant speed v along the dashed line y equals a. When the x-coordinate of the particle is x sub x naught, the magnitude of the angular momentum of the particle with respect to the origin of the system is.
So in this situation, how do you find the angular momentum?
You'd be
Mm-hmm.
you'd use the v equals omega r to substitute or yeah, v equals r omega and then set omega equal to v over r maybe, and then substitute for I wait. Actually, wait, never mind, never mind. I see what I did wrong.
So I think what equation do you want to use?
R cross P.
Mm.
So like L equals RP sine theta.
Yeah. So what's the R?
It's the x square root of x initial squared plus a squared.
Okay.
Like Pythagorean theorem.
Okay. And then what do you get for the angular momentum right now? Outer this R, right? R is the square root of a squared plus x squared. But angular momentum equals RP sine theta. So it will be equal to MV R sine theta. What do you get?
Omega is equal to MVA.
Yeah, so you'll get MVA. Got it?
Yeah.
You got it? Yeah. You done right? Okay. So rotational angular momentum we go through already. So can you do did I include a file here? So I can upload a file. I think last time you already get a file, right? Do you? The
Yeah.
rotation, kinematic, rotation packet, you already have it, right? Do you get it already? So make sure I spend some time to work on it. It's okay? This is APC rotation. This one, you can download it. Okay? Right? So this question, we talk about some more the questions, so you can review. And then this question is similar, you can work on it, right? Work on it first, and then next time we'll talk about lab design questions. The rotation should be done. Is okay? Okay.